Welcome, everyone, to the Segrè lecture. My name is Wick Haxton. I'm the chair of the Berkeley Physics Department, and thus have the great pleasure to welcome you this evening to our distinguished lecture. Berkeley Physics has a distinguished history. It's marked by both world-class research and dedicated to a public mission, making higher education more accessible to California citizens. We are really proud to be part of the world's finest public university. Our department's rich history includes Ernest Lawrence's invention of the cyclotron, which gave birth to the field of high-energy physics. It includes Robert Oppenheimer, who attracted to Berkeley a generation of brilliant theorists. And it also includes the person that we honor tonight, experimentalist Emilio Segrè. Each fall, we celebrate Segrè by bringing to Berkeley renowned experimentalists who, through their research, have changed the way we view and perceive our world. Past Segrè lecturers include Nobel laureates Bert Richter, Masatoshi Koshiba, Stephen Shu, Hans Bethe, Art McDonald, David Wineland, Ray Weiss, and Taka Kajita. They include Millie Dresselhaus and Robert Sokolow, and last year's lecturer, Zhaowei Zhuang. And they include department member and former Chancellor, Robert Bergeneau. Segrè received his doctorate in July 1928 from the University of Rome, where he worked with Enrico Fermi. After 2 years in the military, he returned to Rome, becoming an assistant professor in 1932. In 1935, Segrè became a professor and director of the physics laboratory of the University of Palermo. Soon after, he made his first visit to Berkeley. Lawrence gave Segrè a strip of molybdenum that had been irradiated in his cyclotron. In Palermo, Segrè and his close colleague, Perrier, extracted from that strip a previously unknown and unstable element, technetium. This was the first discovery of an artificial element, an element that could not have survived from the Big Bang, an element that was absent in nature. Just 15 years later, this had a big impact in astrophysics because technetium was discovered in stellar atmospheres, and that proved that certain stars must continually synthesize heavy elements. In the summer of 1938, Segrè returned to Berkeley to continue his work. While he was in the US, Mussolini's government passed laws that barred Segrè and other Jews from universities. Lawrence offered Segrè a position as a research associate, and Segrè accepted. He brought his wife and his young son from Italy to join him. With the war depleting Berkeley faculty ranks, Segrè became a lecturer in the department in 1941. In 1943, he accepted Oppenheimer's invitation to join the Manhattan Project at Los Alamos, where he headed a group that measured fission rates. He returned to Berkeley after the war ended. In 1955, Lawrence and colleagues designed the Bevatron to produce 6 GeV protons, an energy that was selected because protons interacting with the target could produce proton-antiproton pairs. Later that year, the discovery of the antiproton was announced in a paper by Chamberlain, Segrè, Huygens, and Ypsilantis. Chamberlain and Segrè were awarded the Nobel Prize for this discovery in 1959. After that, Segrè continued teaching in the department and doing his research at Berkeley to and beyond his retirement, which was in 1972. Over his 5-decade association with Berkeley, Segrè trained 30 PhD students, including C.S. Wu, Herb York, Tom Ypsilantis, and Herb Steiner. And I just saw Herb Steiner here tonight. In 1989, at the age of 84, Emilio Segrè died from a heart attack while walking near his home in Lafayette. Segrè was an avid photographer. After his death, much of his physics collection was donated to the American Institute of Physics, preserving a record of physics before, during, and after the war years. So now it's my great pleasure to invite my colleague and Berkeley professor John Clark to introduce tonight's distinguished speaker. Thank you.
Well, good afternoon, ladies and gentlemen. I'm privileged and delighted to introduce Professor Jocelyn Bell Burnell to present this year's Segrè Lecture. She is extremely well known for her discovery of pulsars while she was a graduate student in radio astronomy at Cambridge University, opening up an entirely new branch of astrophysics. This, of course, will be the subject of our lecture tonight. In fact, the two of us overlapped for a couple of years as graduate students at Cambridge, although in different departments. Professor Bell Burnell received her bachelor's degree in physics from the University of Glasgow in 1965 and her PhD from Cambridge in 1969. She held several academic positions before her current appointments as Chancellor of the University of Dundee and visiting professor of astrophysics at the University of Oxford. During her career, she has held many other distinguished leadership positions. These include President of the Royal Astronomical Society, the first female president of the Institute of Physics of the UK, the first female president of the Royal Society of Edinburgh. She was also project manager for the James Clerk Maxwell Telescope on Mauna Kea in Hawaii. In recognition of her pioneering research and many leadership roles, Professor Bell Burnell has received an enormous number of honors and awards, far more than I can possibly describe in a reasonable length of time. And I've tried to pick just some of the highlights. In the UK, she is a Fellow of the Royal Society, a Fellow of the Royal Society of Edinburgh, the Fellow of the Royal Astronomical Society, and a Fellow of the Institute of Physics. In 1999, she was appointed Commander of the Order of the British Empire, that is a CBE, for her services to astronomy, and subsequently promoted to Dame Commander of the Order of the British Empire, a DBE, in 2007. In the US, she is a Fellow of the American Academy of Arts and Sciences and a member of the American Philosophical Society. Among her many awards, she has received the following: the Michelson Medal of the Franklin Institute of Philadelphia, the Tinsley Prize of the American Astronomical Society, the Herschel Medal of the Royal Astronomical Society, the Magellanic Premium of the American Philosophical Society, the Royal Medal of the Royal Society, the Woman of the Year Prudential Lifetime Achievement Award, the Institute of Physics President's Medal, and the Grand Medal of the French Academy of Sciences. Very recently, actually in California, she was awarded the Special Breakthrough Prize in Fundamental Physics. And she donated the prize money, $3 million, to the Institute of Physics to support scholarships for students from underrepresented groups. As a final note, the public appreciation and understanding of science have always been important to Dr. Bell Burnell, and she is much in demand as a speaker and broadcaster. In her spare time, she gardens, listens to choral music, and is active in the Quakers. She has co-edited an anthology of poetry with an astronomical theme as the title, Dark Matter, Poems of Space. Please join me in welcoming Professor Bell Burnell to present this year's Segrè lecture. The title is The Discovery of Pulsars, a Graduate Student's Tale.
Thank you very much, gentlemen, for that generous introduction and for the opportunity to be here to give this Segrè talk. Thank you also to so many of you who've turned up this evening. I'm sure there are better things to do on a lovely Friday evening, but thank you for being here. So I am going to tell a story, the story of the discovery of pulsars. It's a story that's now just over 50 years old, and looking back, Britain felt a rather different place back then. So I'm going to tell you a little bit about radio astronomy, because this is a radio astronomy story. I will have to introduce you briefly to quasars, which are different from pulsars. I'm going to talk a little bit about being in Cambridge, UK, and discovering pulsars, and I'm going to tell you a bit about what pulsars are. But we're starting off with a little bit of basic physics. This is what we call the electromagnetic spectrum, or the family of light. We're all familiar with light. It's how we see things. Light is a very small component of a much larger spectrum that we have been largely unaware of until quite recently. In the middle, we have the whole spectrum. This little rainbow in the middle is the bit that we can see, the bit that our eyes cover. And there's a lot else as well. We now do astronomy right across this whole range, and being able to work across such a wide range has delivered all sorts of riches. But I'm going to be talking primarily about radio astronomy, which is at the left-hand end. So here's the visible spectrum, ranging from purple to red. If you go out the red end of the spectrum, you come to infrared, which we can't see but is there. If you keep going, you come to millimeter waves. You'll be aware of these. Televisions often operate at that sort of wavelength. So do microwave ovens. So does radar. So do many things in the universe. You can do astronomy at those wavelengths. And if you keep going, you come to radio astronomy. Radio's been around a long time. Radio astronomy developed after World War II. Starting about 1945, some of the people who had worked in radar during the war took the radar receiving equipment, not the transmitting, just the receiving equipment, and turned it towards the sky to see if they could pick up radio waves from anything in the sky. And they could, and they did, and that was the beginning of radio astronomy, which has come quite a long way since 1945. Some of you may be aware of a recent announcement about gravitational radiation. That is not showing on this spectrum because it's a completely different spectrum. It's like there's another slide behind this one. That's the gravitational wave spectrum. And that's rapidly developing and is also going to be as big a spectrum, I think, as this one, given a century or so. As I say, radio astronomy started following the Second World War. This is one of the very old observatories. It's in Britain. It's at a place called Jodrell Bank. And this was the largest radio telescope when it was built in 1957. It nearly bankrupted the place, but the Russians were very collaborative and launched a satellite called Sputnik. And this, with its large collecting area, was able to pick up signals from Sputnik. And suddenly it wasn't an issue that it was overspent and blah, blah, blah. So, quasars. The early radio astronomers turned their telescopes to the sky, their radio telescopes, and found, yeah, there's something sending out radio signals from there, and there's something there, and there's something there. And they began to map the sky. And there were a number of very bright sources, the brightest things they could see. They asked their optical astronomy colleagues, what is there there, and there, and there? And the optical astronomer said, well, there's something that looks like a star, only it's a bit of a peculiar star. We don't really know what it is. So these things became known as quasi-stellar radio sources, or quasar for short. And for a long time, we didn't know what they were, except that they were very strong radio emitters. And then at Caltech, Greenstein and I've temporarily forgotten his name, never mind, it'll come back in a moment. We're studying the optical spectra of a couple of these objects. And
they could see some lines, and that's quite usual in optical spectra, but the lines were in the wrong place. And they suddenly twigged that the lines would be in the right place if they weren't shifted, because whatever it was moving away from us at a large speed. It had a large redshift. It was a spectrum of hydrogen with a huge redshift. Now, in astrophysics, we know that we live in an expanding universe, and the expansion gets faster the further out you go. So if you can work out how fast something is moving away from you, you can work out how far away it is. And these things had such high velocities away from us that they were at huge distances. But they're bright. Generally speaking, distant things are faint. Think of a row of street lamps. The nearby ones are bright, the far away ones are fainter. Well, these things weren't playing the game properly, or they had to be incredibly bright in themselves so that even when they were far away from us, they still seemed bright. So clearly these quasars were really very peculiar things. So slight change of tack. This is the tale of a graduate student, so I'm going to give you just a tiny bit of background. This is a map of the British Isles, you've doubtless worked out. I started life in the north of Ireland. You hear quite a bit about that at the moment because of Brexit and the border. It's this border that they're talking about. I had some of my high school education in the north of England. I did my bachelor's degree in Glasgow in Scotland. Now this brownie stuff is mountainous. So the north and west of Britain tends to be mountainous and not the most affluent. The really affluent stuff is down here in the southeast, where there is the capital city, London. I had decided that I wanted to be an astronomer, a radio astronomer. And following my first degree, my bachelor's degree, I looked for a place to do radio astronomy. I tried first at Jodrell Bank, but I had been told that they weren't going to take women, so when they didn't reply, I thought, right, that's their way of not taking women. Probably the next best place, I thought, would be to go to Australia, to Sydney, where they did a lot of radio astronomy. But as you probably know, the academic year in the Southern Hemisphere doesn't start till January, February. And I had some months in hand. So I thought I'd better put in an application to Cambridge just in case, but I don't think I'll get in there. And hugely to my surprise, I got a place. So this kid who's only been in the north and west of the UK suddenly finds herself down here in the affluent southeast. Stop and ask yourself whose perspective that's labelled. So I turn up in Cambridge, which is away down here, and boy, they are clever, and they're suave, and they're confident. And they're quite keen to let you know they're very clever as well. And I quail. I'm not that bright. They've made a mistake admitting me. They're going to find out their mistake, and they're going to send me home. We have a name for this now. Do people know it? Imposter syndrome. Yep. We didn't name it or label it back then, but this was classic imposter syndrome. However, having had quite a fight, which I won't describe, to get this far, I wasn't going to give up and walk away. So I thought, they are going to find out they've made a mistake. They are going to send me away. But until they do so, I will work my very hardest so that when they send me away, I won't have a guilty conscience. I'll know I've done my best. And so I was working very, very hard. It's quite a good way of handling imposter syndrome if you come across people who you think are suffering from it. So I think I've probably said all of this, except in classic imposter syndrome, we do this bottom line also. I'd better leave before they throw me out. I love this quote. I wish I'd known it when I got to Cambridge. Frequently in error, but never in doubt. It's unclear who said it. I've been told Zeldovich, but on Google it's also attributed to Landau. Whoever said it, it's fantastic. And they have a remarkably good command of English for a Russian speaker. My discomfort increased remarkably when, within the first week of arriving, I got presented, well, all grad students in radio astronomy got presented with a set of tools. I say all grad students. There were a few peculiar guys called theoreticians who didn't get given a set of tools, but most of us did. And this is my set of tools. And they are not microelectronics tools. These are for serious, heavy-duty wire working. And that's exactly what we spent a lot of time doing. I was I chose to be attached to Tony Hewish, who had a program to search for quasars. Remember the quasars? Using quite long-wave radio wavelengths. And to do that, we needed a very large radio telescope. I will explain a bit more about the details in a minute or two. This is near the end of the project. It took 2 years, most of it working in the field. My main job was all the cables, all the connectors, all the transformers. And here I, thoroughly disguised, and my technical assistant, Don, are checking the impedance of some low-loss cable, which you could not coil up and take indoors. It was an airspace cable. I worked through the winter in this little hut or that little hut, putting the plugs and sockets on each end of the cable. And we're checking that there's no dry joints using a slotted waveguide. The radio telescope was huge. It covered an area of 57 tennis courts. It was relatively cheap. Tony had got a grant of £12,000, which, to give you some context, at that stage would have bought starter homes for 3 newly married couples. So it's not hugely expensive as major projects go. 6 people worked for 2 years to build it, and this is the finished object. It looks homemade. It is homemade. 81.5 megahertz, 2048 half wavelengths antennas. That's the layout for those who are really interested. What you see most visibly are the 1,000+ wooden posts. There's 120 miles of wire and cable, and it is actually an interferometer. The two halves are electrically separate, and it could be phased to swing in altitude. With all the wooden posts, it's firmly rooted in the ground, and it depends on the rotation of the Earth to see different bits of sky. So you could steer it in this dimension, and the Earth's rotation did that dimension. They were still using vacuum tube receivers at that point. I'd used transistors in an undergraduate project and said, "Why are you using vacuum tubes?" I said, "Whoa, transistors are noisy. Whoa, transistors are unreliable. We use vacuum tubes." They did ultimately change. Now, the purpose of this whole exercise is to find more of those quasars, those very distant, very strong radio sources. And it used a rather neat technique. You perhaps have been told that if you look at the night sky, the way you tell the difference between stars and planets is that stars twinkle and planets have a steady light. It's because although planets are smaller intrinsically than stars, the planets are much closer and they have a bigger angular diameter. The star, although intrinsically larger, is much further away, so it's much more compact. So compact things will twinkle and extended things will not. There's a radio analogy. Compact things like quasars will twinkle, and the big extended radio galaxies will not. And this telescope was to look for twinkling quasars. So here's a radio telescope. I hope you can see this pointer. I'm on this part, and about halfway down, there's a radio telescope. Way up in the ceiling, far, far away, there is a quasar. And the radio signal from the quasar, as it comes to the radio telescope, passes through part of the solar system. And the solar system is full of plasma coming out from the sun. Electrons, clouds of electrons and positrons, but the electrons are the ones that matter for this story. And those electrons are not smooth, but they're in what I've drawn as clouds. And as the radio wave from this distant quasar passes through the clouds to the radio telescope, sometimes it's going through clouds, sometimes it's going through a gap between clouds, and the brightness of the radio source appears to jump up and down quite fast, as in the bottom right. Radio galaxies, which are extended things, bring down a whole raft of radio waves, and you see some of them through clouds and some of them through gaps, all at the same time. And because you're seeing through clouds and gaps all at the same time, the fact that the clouds are moving sideways has rather minimal effect. So, if you look for radio sources that twinkle, they're most likely quasars. They're certainly compact. And so the idea of this whole operation was to look for radio sources that twinkled, and those should be quasars. But to follow the twinkling, because it's rapid, you need quite a short time constant. And a short integration time, a short time constant, makes the signal to noise lousy. So the only way to boost the signal to noise is to have this enormous radio telescope and collect lots more signal. So that's why we had this huge radio telescope. It covered, I don't think you use acres here, it covered 4 acres, or 57 tennis courts, and was known as the 4-acre array. So the technique was very neat. Survey the sky, find the radio sources that twinkle, that change in brightness, and there's your quasar. The nearest analogy to this twinkling, and apologies physicists, it's not a perfect analogy, is the pattern you can see on the bottom of a swimming pool. If you imagine yourself lying on the bottom of the swimming pool and there's a gentle wind, this pattern of light and dark blows across over your face and you see the brightening and the dimming. Similarly, in the radio waves, as the solar wind carries those clouds of electrons out, you see the brightening and dimming of the quasars. So at the time I started, there were only about 20 quasars known, and it wasn't enough. The idea was to pick them out by their rapid twinkling, so you operate with a huge antennae and a short time constant. And I spent the first 2 years of my 3-year studentship helping build the radio telescope. I then was the person who was the first user of the telescope, so I debugged it and I observed for 6 months, and then spent the final 6 months completing the data analysis and writing up the thesis. And it was successful. I found about 180 more quasars. So the number went up from 20 to 200, which is a good size sample. And I stumbled on something else, well, several other things along the way. At that time, the University of Cambridge had one computer. It took up a room that would be about the size of a quarter of this room, and it had less memory than your laptop. So clearly, there could not be many users. Martin Ryle, who headed the group, had time on it, or his group had time on it, because they were doing Fourier inversions. And doing Fourier inversions by hand is a bit painful. A computer helps. But every other academic in radio astronomy had grad students instead of access to the computer. And our data came out on rolls and rolls of paper. There were actually 3 pen traces. On this slide, you can only see the center one, but there were 3. The telescope produced 30 meters of this chart paper every day. We did a complete sky scan in 4 days, so 120 meters per sky scan. And I operated it for 6 months, by which time I had 3 1/3 miles of this stuff in total. There were lots of scintillating quasars. They showed up very, very nicely. I was able to log them. There were actually very few problems debugging initially. It worked very well right from the beginning. It's one of the few radio telescopes in the world that worked the first time it was switched on. And I give credit to Don Rolfe, our technical assistant that you saw in one of the earlier slides. He wouldn't let us academics take shortcuts. And I think because of that telescope worked beautifully right from the start. But I was looking very carefully at it in order to make sure I really understood what it was doing and that it was doing what it was meant to be doing. I was also looking very carefully at the data because I was sure they were going to throw me out, and until I, you know that bit. And just occasionally, there was a little bit of signal that I couldn't properly classify. There were the twinkling quasars, sure. There was also inevitably radio interference. Particularly back then, cars were badly suppressed. We weren't allowed to drive cars on the observatory site, but if a particularly badly suppressed one went down a local road, I'd pick up the interference. Anything that sparks give radio waves. So arc welders, sparking thermostats, power line sparking. And we also had trouble with pirate radio stations. There are bands of the spectrum that are kept clear of broadcasts for the radio astronomers, and the pirate radio stations thought these were a gift from heaven. So you got used to identifying interference. But this peculiar little signal, which only occupied about a 1/4 inch, or 10 parts in a million in terms of total length, didn't quite look like a scintillating quasar, didn't quite look like interference. And for those sitting near the front, I can explain why. Apologies to people further back. You may not be able to see enough. This bit here, right of center, is some low-level interference. And on the left-hand edge is one of the, in fact, the first tracing of the first pulsar. And I can look at that and say, it looks different. It's not interference. The interference, there's space between the spikes. You can see chart paper between the spikes. You can't here. With the interference, the spikes go up and down. Here, they go largely up. They don't look the same. When you're doing that kind of analysis about whether you can see paper between the spikes or not, or whether you're saying the spikes go up and not down, this is Fourier analysis that you are doing. You're commenting on the frequencies present. Can you see chart paper between the spikes? Is it low frequency? And you're commenting on the amplitudes. Do the spikes only go up or do they go up and down? So subconsciously you're doing Fourier analysis. But put crudely, it looks different. And this early in the project, I had so many things to deal with, I simply logged it with a question mark and passed on. But after this had happened, and it didn't automatically happen every time, but after I'd seen it a few times, my brain said, "You've seen something like this before, haven't you? You've seen something like this before from this bit of the sky, haven't you?" And then it's easy. I file the rolls of chart paper by which strip of sky, the declination we're looking at. They're filed in shoeboxes. So I go get the shoebox for this strip of sky. I find a large area of floor. This would be splendid. And you spread out and you line them up by the stellar time. You know the stars? Maybe you don't know. The stars don't keep a 24-hour clock. How you've probably noticed this is you may have noticed that the constellations in the night sky in summertime are different from the constellations of stars in the night sky in wintertime. That's because the stars get 4 minutes earlier every day. That's 28 minutes a week, and over the months that accumulates. So I line up these charts by the star time, and yep, that's that one. Wasn't there that time we looked, wasn't there? Oh, it might have been there. It's a bit low level. Yep, I logged that one with a question mark. No. And here's this one. And look, they all line up, the same sidereal time. It's keeping its place amongst the stars, whatever it is. So in naive excitement, I go to my supervisor and say, "Tony, look at this." And he says, "It only occupies 1/4 of an inch. You can't see what's going on. We need an enlargement." With this technology, enlargement is easy. You run the paper under the pen faster and it all gets spread out. So we just switch to high-speed recording, easy. No. The roll of paper runs out in 20 minutes. And guess who lives at the observatory day and night putting a fresh roll of paper in every 20 minutes? Next best idea. The grad student goes out to the observatory at this time, switches to high speed, switches back to normal at this time, and the survey continues. So that was my mission, and I did it for a month, and the thing had disappeared, and I was making high-speed recordings of this sort of guff, which is just receiver noise. And my thesis advisor, Tony, got very cross. "It's a flare star, it's been and gone and done it, and you've missed it." Grad students, past and present, you probably recognize this. It's always the grad student's fault. I skipped one day after a month of this, went out to the observatory next day, and it had reappeared. I didn't dare leave, I stayed on, and in came this. The bottom trace is 1 second time pips, and the upper trace is what we picked up. That labeling comes later, as I'll explain shortly. And there's a good run of pulses here in the middle, pulse, 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 pulse. You can see it's beating at a period of about 1 1/3 seconds. There's one missing here, and there are several missing here, but it comes back on beat. It keeps the phase. So the strength of the pulse changes dramatically, but it keeps the beat, it keeps the period. I telephoned my supervisor, who at that point was teaching in an undergraduate laboratory, and he was an optics laboratory. He's probably dealing with some twit of an undergraduate. There are a few in Cambridge who thinks his diffraction grating has 1 line per inch. And then his twit of a grad student phones up and says, "Hey, Tony, you know that funny signal? It's a string of pulses 1 1/3 seconds apart." Huh, must be man-made. Came out to the observatory next day at the appropriate time, stood looking over my shoulder. Really scary. It had been missing for a month. It had appeared the day I missed it. It appeared the day I got it. Would it be there 3 days in a row? It was. He saw it for himself. And we quickly established that the period was the same as the day before. So at least on a 24-hour time scale, it wasn't tiring. So, because it moves around with the stars, it keeps this 23-hour, 56-minute day, it's unlikely to be radio interference. It's not Joe Doak driving home from work in a badly suppressed car, because he's getting off work 4 minutes earlier each day, 28 minutes a week, and this has been going on for several months. In fact, the only humans who keep that timetable are other astronomers. But nobody else does. So the first question we addressed was, has Jocelyn wired the radio telescope up wrong? It's always the grad student's fault. We got another academic and grad student in the group who had a separate radio telescope and separate receiver, also working at the same frequency. And we asked them to see if they could pick up this signal. We were fairly confidential about this because Tony was fairly certain the grad student was being stupid and we were all going to make fools of ourselves. So we were fairly discreet about this. And I remember that vividly. Paul Scott was the other academic, Robin Collins, his grad student. And the two telescopes were slightly differently aligned. It was seen first by my telescope. It was pulsing nicely that day, bless it. And then we went and stood by Robin's chart recorder, and it should have appeared 5 minutes later. And nothing happened. And the two academics, Tony and Paul, started walking down this long lab, and I was padding along behind them, trying to keep up in every sense of the word. Robin stayed by his pen recorder. What could it be that shows in our radio telescope, but not? Could it be? No, it can't be that. But you think, no, that wouldn't work. What about? Yeah. Here it is! Came the shriek from the far end. We came charging back up, and Robin's telescope was picking up a pulsing signal with a period of 1 1/3 seconds. We had miscalculated by 5 minutes when the second telescope had seen it. If we had miscalculated by 25 minutes, we'd have all gone home and the story would be different. But it's not a fault of the first radio telescope or receiver, because a separate radio telescope and receiver picks it up. It's a puzzle because the pulses are short. Particularly, they've got sharp rise time and fall time, which means the object has to be small. But it's keeping the same pulse period. It's not getting tired. It's got great reserves, so it's big. So it's big and it's small. Yippee. With time, we managed to sharpen that statement. It's big in terms of mass. That gives it the reserves of energy. It's small in terms of overall size, diameter. That's what gives it the sharp rise and fall times. But it took us a while to get clear on that. A colleague, John Pilkington, managed to get a dispersion measurement. You'll have seen the dispersion of light. It's when you get a rainbow. Light going through a raindrop splits into its constituent colors. There is an equivalent phenomenon in radio. High frequencies travel slightly faster than low frequencies if the radio wave goes past any free electrons. And John Pilkington took two of my receivers, tuned one of them up to the top of the band and the other down to the bottom of the band, So we had one at about 82 megahertz and one at about 80 megahertz. And after a number of false attempts, finally managed to prove that the signal appeared first in the high frequency receiver and a little bit later in the low frequency. And by the time delay and making a guess how many electrons, or making a guess at the electron density out in space, got an estimate of the distance. And it came out at about a couple of 100 light years. That puts it well within our galaxy, but way beyond the sun and the solar system. So it's not other astronomers here on Earth causing interference. This was the point where I started labeling it LGM, for little green men. It was really rather a mouthful. You know that funny pulsing source at 1919 plus 20 something became LGM. I think it maybe wasn't wise, but I did it. So another test we tried is if it really is little green men, they probably live on a planet, and their planet is going round their sun. So you're all radio astronomers, and I'm a little green man, and some of the time I'm coming towards you, and some of the time I'm coming away from you. And when I'm coming towards you, the pulses pile up on each other, and they're closer than 1 1/3 seconds. And when I'm moving away from you, they're stretched out. So we started, well, I had to do it, making regular observations of the pulse period to look for this, what's called Doppler shift. It's not quite that simple. You're now the pulsar, and I'm a radio astronomer here on Earth. The Earth goes round the sun. And as the Earth is moving this way, I see your pulse period stretched out. And when the Earth is moving this way, I see your pulse period compressed, shortened. And we found that. So we proved that the Earth went round the sun, but otherwise weren't making huge progress. Until just before Christmas. This is now about 3 weeks after the detection of the first one. And it's just before the Christmas break, and I go down late in the afternoon to Tony's office to ask him something. And rather unusually, the door is shut. So I knock. Come in. Ah, Jocelyn, come in and shut the door. So I went in and shut the door. And there was Tony, my supervisor. There was Martin Ryle, the professor who headed the group. And there was John Shakeshaft, who was editor of one of the journals. And it was a discussion that I think I should have been part of right from the beginning. How do we publish this? We've only got one. We've done just about all the tests we can think of doing. And we've, consulted more people in the radio astronomy group with time for ideas. We don't know what it is. We don't think it's interference or terrestrial. We think it's genuine cosmic. But how can we convince editors of journals, let alone other astronomers? We didn't solve it that evening, and I went home for some nourishment, really very cross. Here am I trying to get a thesis. My money's running out in 6 months, and some silly lot of little green men has to use my frequency and my radio telescope to signal to Earth. Come back in that evening to do some more data analysis, because the routine data analysis is falling oodles behind. Grad students didn't have keys to the lab. Come 10 o'clock, the janitor locked up. You could be locked in or locked out, your choice, but you had no key. And it was fairly important that I was not locked in, because my boyfriend and I were going off early next morning to Ireland to announce our engagement. And you can't, he and she have to be there together for that. 5 to 10, shortly before locking up, I'm busy scanning through another part of the chart recording. For the astronomers in the audience, it was when Cassiopeia A was on the northern horizon. And in Britain, you can see Cassiopeia A both when it's due south and when it has rotated around to be low on the northern horizon. And with my kind of radio telescope, a strong source like that can be seen through the back of the telescope. So there was always 20 minutes worth of chart where the pen did due to Cassiopeia A on the northern horizon, and I just, scrapped that bit. So I come to one of these bits, and there's a quiet bit in the middle, and that couldn't be another one, could it? In the middle of Cassiopeia A lower culmination, yuck. 5 to 10. Get out the shoebox that covers that bit of sky, throw the charts out. Cass A mess, Cass A mess, Cass A mess. Might be there. Mess, mess, mess. Could be. Mess, mess, mess. This one. And they line up. And that bit of sky is going through the telescope beam at 2 o'clock in the morning, and I've got to be there to do a fast recording. Throw the charts on the desk, rush out of the laboratory as the janitor's locking the doors behind me. Go out to the observatory at 2 o'clock in the morning when that bit of sky was being viewed by the telescope. 21st of December, really cold. And when it was really cold, there was a dry joint that shrunk. And the thing was working at half strength. So I breathed on it, I kicked it, I swore at it, I flicked switches. I got it to work for 5 minutes at full strength, and it was the right 5 minutes and the right setting, and in came pulse, 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 pulse. This time, 1.2 seconds. The first one was 1.33. Similar beastie, totally different bit of sky. There aren't 2 lots of little green men on opposite parts of the sky, both deciding to signal to planet Earth using a stupid technique. This is some natural phenomenon. I left a message for Tony, went back to Ireland with my boyfriend. We announced our engagement, and I came back in early January, sporting an engagement ring, which I was so proud of that I wore into the lab. That was daft. It signalled that I was quitting, because married women didn't work in Britain at that time. And I thought I was probably continuing to work, but I hadn't thought it through, and I hadn't thought the implications of wearing a ring. Tony had kept the survey going, which meant he'd put fresh ink in the inkwells, fresh paper in the pen recorders, and piled the rolls of paper on my desk for analysis. And he was in a meeting when I got there. I couldn't immediately find him, but clearly there was work to do. So I sat down and started doing some more of this chart analysis. And I'm working merrily through, oh yes, which one's that? It's not either. No, it can't be either. Gosh, is it another one? Okay, there's only about another 5 foot of this chart. I'll just finish this. So move on. What? 2 of them? About a yard apart? On the one beam setting? At this point, Tony appears and stands at the end of my desk. Oh, look, Tony, look. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look at these. Huh. How many more have you missed? Go back through all your old records. I did go back through all the old records. I didn't find any more candidates. We confirmed those 2 over the next few weeks. And so we had 4, and so we could publish. We had the first paper written. It went out first, and then the other 3 came along soon afterwards. It attracted a lot of press attention, which I wasn't entirely happy about. One of them asked, had we ever considered calling these, or did we ever consider it could be from little green men? And being naive, truthful academics, we said yes, and that increased the press attention. it was also very sobering for a young woman at that time. Typically, they'd interview Tony and I together. They'd ask Tony about the astrophysical significance, and then they turned to me for the human interest. What were my measurements? How tall was I? Would I describe my hair as brunette or blonde? How many boyfriends did I have? And the photographers would say, could I undo some buttons, please? It was absolutely horrible. And I would have loved to be very, very rude to them. But I'm a grad student whose money's running out, who's nowhere yet near finishing her data analysis, let alone writing her thesis, and she needs references from the department. So I kind of had to stomach it, but it wasn't nice. The name Pulsar was coined by one of those newspaper science correspondents from a rather conservative British newspaper called the Daily Telegraph, but with quite a good science correspondent. And it was he who suggested Pulsar, by analogy with Quasar. He asked us what we thought we were going to call it, and we thought we had thought about this, because we, in writing the first paper, had had a long discussion. Are these things described as pulsating radio sources or pulsed radio sources? And we decided on pulsating because pulsed could imply an agency, some little green men making the signal pulsed. So we thought we knew the answer to that, but he was looking for something shorter, and so pulsars they became. So, what are these pulsars? They're tiny, tiny objects that about 10 miles across that spin. They have a very strong magnetic field. Stationary one perhaps explains it better. Spin axis vertical, magnetic field offset, and from out of the magnetic poles, these cones, come these beams that swing round the sky like lighthouse beams. And if the beam shines in your face, you see a pulse. So one of those beams, that one, shines, but that one does not. There is one object where we think we see both beams, but mostly you only see one. They're very small, very dense, rich in the particles called neutrons, so they're sometimes called neutron stars. They have 1,000 million tons jammed into a ball 10 miles across. To say they are very dense is an understatement. They have amazing physics because of their density. They have very strong gravitational fields. They also have hugely strong electric and magnetic fields. And we believe they're formed when a massive star, much bigger than the sun, something like Betelgeuse, when it reaches the end of its life, it explodes, and the core of the star gets shrunk in the explosion, spins up, and becomes one of these pulsars. If you listened to one of them, here's hoping this works. So that's a pulsar spinning 11 times a second, 660 revs per minute. Sounds a bit like a roughly running truck. That's because the internal combustion engine idles at around 700 RPM, and this is doing 660. But there's quite a range of periods of these things. They're seen primarily in the radio. We're pushing 3,000 of them now known, really very few in the visible, a number in the X-ray, and a surprisingly large number in gamma rays, for reasons that we don't fully understand. Many stars up in the sky are twinned in binaries, and about 10% of these pulsars are in binaries. One of the binaries is two pulsars together, and they orbit each other every 2.5 hours. So there's some very good, very strong gravitational fields, very strong magnetic fields, a lot of very interesting physics in that system. We also have a triple system. That's very useful for testing Einstein's theories about, no, I need to backtrack slightly. The triple system consists of a pulsar and a different kind of compact star called a white dwarf, orbiting each other, and the pair are orbiting another star in the middle. This is useful for testing another of Einstein's theories. You perhaps were told that Galileo dropped things off the Leaning Tower of Pisa to see if they fell at the same rate. He started with two balls of the same size and different mass. They fell at the same rate. He then tried two balls of different composition. They fell at the same rate. It's said that he used something like a hammer and a feather. That's nonsense, because if you try dropping a hammer and a feather, the hammer goes chonk, and the feather goes woof, 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 woof. The astronauts on the moon repeated that experiment where there's no air, and the hammer and the feather fall at the same time. Now, with this triple pulsar system, pulsar and a white dwarf, a different kind of star, like hammer and feather, moving in the gravity of the central star. Do they move the same way in the gravity? Will they keep in the same orbit? Or does one of them get pulled more towards the central star than the other? Difficult measurement to do. It's a close call. Probably Einstein's correct, as far as we can see. This is a photograph of a nearby small galaxy called the Magellanic Cloud, the Large Magellanic Cloud. Lots of stars, lots of red hydrogen gas. You quite often see red splodges in astronomical photographs. It's hydrogen, always. So when you see a red splodge, you say, ha, hydrogen. And you'll be right 99% of the time, because it's 99% of the universe. One little star here has been picked out with an arrow. Just to be absolutely clear, the arrow's added after the photograph's taken. Here in the bottom right is the star that needed picking out with an arrow. It has exploded. It's one of these supernova explosions, the kind of thing where we think pulsars are created. Pink stuff being hydrogen. Hydrogen makes up 98% of the universe, so you see pink splodges everywhere in astronomical photographs. This is the remains of another star that exploded, observed by the Chinese in 1054 AD. There's a pulsar in the middle, and the pulsar is keeping the nebula shining. One of the great problems used to be, why does this nebula keep shining? Why isn't it fading? Because there's a pulsar in the middle. So these things are typical star mass, about 1,000 million tons. It's got a radius of only 10 kilometers, which means its density is comparable with the density of the nucleus of the atom. And it's rich in neutrons, hence the name neutron star. To give you a feel for that density, take a thimble, a sewing thimble, nice silver one, take the population of the globe, jam them into the thimble. When you've got it full of people, it weighs the same as if it was full of stuff from one of these stars. It's really, really dense. Fantastic, interesting physics as a consequence. The strong gravity means that any light near these things gets bent. So I could be on the surface of one of these stars without moving my feet. I can see 3/4 or 2/3 of the surface of the star because the gravity bends the light. The gravity also affects clocks. You know this already. Your phone, your sat-nav, uses signals from satellites up in space in a lower gravity environment than here. Your phone, your sat-nav, corrects for the fact that the clock here on Earth goes slower than the clock up in the satellite. It knows about Einstein's general relativity. Same thing happens on a pulsar. I'm going in to land on one of these pulsars. I'm landing feet first because it's the ladylike way to do so. There's a strong pull of gravity. There's a stronger pull on my feet than on my head. and my body gets stretched. Indeed, my body gets overstretched and pulled apart. Feet fall in first, shins next, knees and thighs, etc. thereafter. Don't go visit a pulsar. Very strong magnetic field, and if you spin an electric field, you get a voltage drop. You get electric fields of about 100 million Tesla, voltage drops of 10 billion volts per centimeter. These create forces that are even stronger than gravity. But when you get a body of that mass spinning, it's the devil's own job to make it change its spin. It just keeps going. And so these beams, these pulses come round and round and round and round, and you've got a superb ticking clock. In fact, we've now got 3,000 of them dotted throughout the galaxy. And we're using them to do other tests of Einstein's relativity. I'm going to skip that, and I'm going to skip that. There are new telescopes coming along. I'm going to finish with some crazy pulsar records. The pressure at the center of one of these stars is large. The fastest known pulsar, that's its, so to speak, name. Look at this period. Look at the accuracy with which it's measured. That's in milliseconds, thousandths of a second. And actually that 3 at the end is not all experimental error, because the period is actually slowing. The period is increasing just a little bit. This is the fastest known one so far, and if you were to listen to it, it sounds like your kitchen blender. It's going so fast. The Nobel Prize this year went, the physics one, half of it went to some Europeans who had discovered planets around other stars. The Nobel Committee got it wrong. The first planets around another star were planets discovered around a pulsar. As the planets orbit the pulsar, they tug it around. That produces minor changes in the period. And if you measure the period accurately, you can work out that it's got 3 planets, 2 big ones, 3 planets and a tiny 4th one. Quite a complicated system. Why a pulsar has planets, how planets survive around a pulsar, I don't know. And so far this seems to be the only system that does of planets. So maybe it's got a special history. The roundest known thing in the universe is the orbit of a pulsar round its companion star. The orbit's round to 5 microns, which is 1/10 the width of a human hair, and the whole orbit is over 500,000 kilometers. For those of you that teach conics, the eccentricity is about 10 to the minus 7. And if something falls onto the surface of a pulsar, it hits the deck, traveling at half the speed of light, having started from just a meter or 2 above the surface. These things are fun. Thank you for your interest and your attention.
Thank you for this utterly wonderful, beautiful, marvelous talk. It was so beautifully delivered, and I think we were all totally fascinated by it. Does anyone have a question?
Can you eliminate the possibility that what causes a pulsar is the atmosphere? That is, the light going through the atmosphere. The atmosphere causes it to twinkle. Can you eliminate that as a possibility?
Yes, because we got about 3,000 of them, and you're beginning to stretch the credibility.
The part of the story I wanted you to get to is when you actually finished your thesis. I know it seemed like we were just moments away from that. Really, how did it go after you were able to participate in the publishing, and then you had this research? How many more months or years did it take to turn that into a thesis?
Oh, well, in the British system, it's a good deal faster than the USA. So in the last 6 months of my 3 years, I wrote the thesis. Tony said it was too late to get the title changed, so it had to be on the scintillating quasars, the twinkling quasars. But I put the pulsars in an appendix, and it's probably the most read appendix of any thesis.
Quick question about that dispersion measurement you were talking about to measure its distance. How do you know whether you're detecting the same pulse or whether you're detecting the next pulse?
Good question. The delay between the two frequencies was only 1/4 of a second, and the pulse period was over 1 second. So we knew it was the same pulse, but fair point. Thank you for that.
This is a question more about the part of your story where you detailed imposter syndrome and that kind of thing. As a woman in physics, that must have been a pretty surmountable challenge. So what I wanted to know is, what drew you to physics in the first place as an undergraduate? Why did you pick radio astronomy specifically? And also, did you have any other experiences in your life as a physicist that kind of brought that distinction to the forefront?
So as soon as we started doing science at school, it was clear I was good at physics, quite good at chemistry, bored by biology. So I focused more and more on physics as I went through school, and I was thinking all the time, okay, it looks as if you're going to do a physics degree. What are you going to do after that? And my father brought some astronomy books home from the public library, and I read them. We were doing circular motion at school, and there was this book about a galaxy that was rotating, and I thought, gee, this stuff can be applied to all this great cosmic stuff. So I decided I was going to be an astronomer, and then I gradually refined that radio astronomy was one of the new developing branches of astronomy. So I decided that that's where I would aim for. But I did a physics degree first, and then went into radio astronomy.
When the positron was discovered, all the physicists went back to their cloud chamber data, and many of them found that they had already seen positrons, but they didn't have the courage, I guess, to publish this as a discovery. After you published on the pulsars, did people go back to their radio astronomy data and find many, many more of them that they had somehow overlooked?
Not quite that, but people recalled instances where somebody had reported pulsing and they'd been ignored. The most striking example of this dates from 1957 at McDonald Observatory in Texas. McDonald specified that that observatory had to be open to the public 1 night per month. It was the open night. The telescope was set on the Crab Nebula and that funny star in the middle that we now know is a pulsar pulsing 30 times a second. And people stepped up to the telescope and said, oh, cool, awesome, whatever people said in 1957. And a young woman stepped up to the telescope and said, that star's flashing. And the night assistant started to explain about scintillation and, the random twinkling. And she stopped him. She said, no, I hold an airplane pilot's license. This is 1957, a young woman. My job is to fly aircraft from the manufacturer to the customer. I fly at night, I know the night sky, I know about scintillation. That star's flashing. Nobody followed up. That pulsar flashes 30 times a second, 30 hertz. Some people, particularly young women, can see 30 hertz. The Canadian power supply used to be at 30 hertz, and people complained so much about the lights and the TV flashing that they went up to 60 hertz. The story is told by a young man who was working there as an intern over the summer. He subsequently became a university professor and told every generation of students he lectured to, follow up anomalies. But that one was not followed up. Yes.
You beautifully anticipated my question. I was asking, are other frequencies also being pulsed as well as radio frequencies? Yes. And you've already answered that.
Yes.
But do these also go to shorter wavelengths as well?
Yes, they do. Relatively few are seen in the optical. That's unusual. X-ray astronomers can see some, and gamma-ray astronomers can see some, but not many in the optical. Now about 3,000 probably in the radio, over a whole range of radio frequencies. How they emit, why they emit, what the mechanism is still a mystery. The physics is very hard because everything is so extreme, says she rapidly to excuse physics colleagues for not yet cracking them.
Hi, I was just wondering, at what point in your career did reporters stop asking unrelated questions?
Well, there was really only that one episode where I tested the waters, so to speak. But for a long time, one particular newspaper had what was notoriously known as page 3, a photograph of a buxom female scantily clad. It's still there, but to a lesser extent. And certainly in academic circles in Britain now, there is very great emphasis on being fair to people, whatever their gender, ethnicity, sex, whatever.
What led you to the conclusion that it was a neutron star because your advisors were looking for white dwarfs at the time?
Yes. Tony was fairly convinced it was a white dwarf. The really crucial thing was if it was a white dwarf, it was an oscillating white dwarf. If it was a neutron star, it was a rotating neutron star. Now, as a rotating thing ages, it gets slower. The period would increase. If it's a vibrating thing, the way vibrating things age is they quiver faster with smaller amplitude and cease. So if it's a vibrating thing, the period gets shorter with time. When 6 months later we got the pulsar in the Crab Nebula, it was sufficiently strong and fast that we were able to measure how the period was changing. And the period was slowing, which meant it was a rotating object. But until then, quite a lot of theories were in play.
I guess that I have something that's seeking
Sorry,
philosophical.
Where's this coming from?
Right.
Yes, sorry.
Yeah,
yes.
a philosophical comment here, but I'm struck with how so much of the physics involved here is wildly out of the realm of human sensibility.
Yeah,
and yet the end result is just, it's just ordinary human experience. A ticking clock, or a buzz.
Yes, yes. The physics of these things is really extreme in every dimension at the same time. Strong gravity, strong electricity, strong magnetism, rapid rotation. It ticks too many boxes at once, frankly.
So what made the pulsars disappear for months at a time?
Oh, thank you. Yes, I didn't explain that. Remember that the original thesis was looking at how the signal from quasars fluctuated in brightness because of the uneven solar wind, the uneven plasma between the sun and the planets. It turns out that there's also uneven planets way out in the galaxy between the stars, but that doesn't produce pulse-to-pulse changes. It produces changes on a timescale of weeks and months. So the pulse-to-pulse stuff is by interplanetary scintillation. The longer-term stuff is a similar but different timescale phenomenon that we call interstellar scintillation. And it's another plasma effect.
It's not radios at all. I'm interested in your opinion about the recent discovery of neutrinos from a blazar, and you probably know the number of that blazar.
Yes, let's go cautiously. As science funding gets tighter, it's always tempting to shout about your result a little too soon. So there have been reports of neutrinos from this or that or something else still to be confirmed. This may or may not be one of those, but a little bit of time will tell us. It would be great to definitely detect neutrinos from some things. It's high time we did, to be honest. So let's hope that this might be really it. But I'd say wait just a little bit more for.
Thank you. I'm curious what the energy output is of the pulsars. Like, do they have a wattage that you can report?
I'm sure they do. I'm not sure I have a figure in my head. I don't think I can answer that without doing a bit of deviling around, I'm afraid.
In terms of like 4 pi steradians of them, how much dispersion do they have out of each end?
The actual beam is a degree or two across, we suspect. It's probably circular, and of course there's 2 beams and we're only seeing 1. But
thank you.
Hi, I was wondering why it was you who detected the pulsar and not the graduate student in the competing telescope, if it was like luck or dedication or just something technical?
It was partly imposter syndrome driving it, to be honest. It would have been awfully easy just to dismiss that 10 parts in a million anomaly. The other telescope that got used in the confirmation was not doing a survey. So the chances of them stumbling on one of these was very, very small. But because I was doing a whole sky survey, or a large chunk of the sky survey, I had more field to work with, if you like. Yeah.
Yes, wonderful talk, by the way. You were the first person to observe pulsars. Yeah. You therefore discovered them. The Nobel Prize was awarded in 1974 for that discovery, but you did not share in it. Mm-hmm. So how do you feel about that?
Well, at the time I said, and I still feel the same, it was a very, very important Nobel Prize. There is no Nobel Prize in astronomy. There is also no Nobel Prize in mathematics. Rumor says it's something to do with the professor of mathematics, the professor of astronomy, and Nobel's wife. But whether that's true or apocryphal, I don't know. But it's true that physics is the only one of those 3 subjects that has a Nobel Prize. And up till then, the physics committee had not considered any work in astronomy worthy of a physics prize. So this was a watershed. And I was very proud that it was my stars that had convinced them that there was good physics in astrophysics. Having said that, and whilst I was, entirely happy about it, a lot of my contemporaries were unhappy, livid, and it became known in Britain amongst the graduate student community as the No-Bell Prize. Since then, about 20 other astrophysicists have had the Nobel Physics Prize. So I was right in my hunch that it was a great precedent.
Hello, thank you for coming down here for the talk. So what I was wondering was how you convert sky is a right ascension and declination, that's 2 dimensions. How did you get that to be one line? What are the axes on that graph?
Are you talking about the positioning of the source?
Well, no, what I'm talking about is your data got output on a single line, or a single pen rather.
Yes.
What are the axes on that graph, and how did you convert the 2 dimensions to sky?
Time runs along because the chart flows under the pen, and the pulses were the strength of the radio signal. Does that make sense? You don't look as if you're convinced.
I guess the other, what I was basically asking was, if sky, you have the 2 dimensions, right? What is that one line looking at? Is it looking at a line across the sky? Or?
Okay, so the radio telescope always points due south and is dependent on the rotation of the Earth for this direction, but you can electrically phase it to swing in altitude. So for the astronomers, this is right ascension, and that is declination. And then, depending on where the thing is pointing, the signal comes in, and the pen chart records the strength of the signal from that bit of sky, and the sky is forever moving past. So basically, you're sampling a strip of sky and seeing how strong the radio signal is.
Thank you.
Hi, thank you also for being here. This is more of a fun question, but I heard that on NASA's Voyager mission, they sent out a pulsar map. I was wondering if you could talk about that and what you thought about it.
Right. If you look closely at the poster for this talk, up in the top right, I think it is, there's something that looks faintly star-shaped. That is taken from the Voyager plaque. But basically what they did with Voyager was they told any little green men who pick up the Voyager satellite where we are and where they need to come and get us. We've always known that pulsars could be used as navigation beacons. You have your spaceship, you have a great radio telescope attached to your spaceship, and as you go around you say, well, there's that pulsar, because each has its own flash rate, and there's that one, and there's that one, so we're here. They've reversed that on the plaque. They show the Earth, they show the direction from the Earth to several pulsars, and they have on the direction line little ticks which give the period of the pulsar in a binary notation. So some little green men pick up a Voyager satellite, and being highly intelligent, they can work out where we are, and actually when the satellite set off, because the periods of the pulsars gradually increase as they age. Yeah.
One last question, gentleman in front.
Hi, lovely talk. You distinguished your pulsars from the radio interference partly because of the Fourier, but partly because of the positivity above the line rather than below the line. Is that because if it's interaction with electrons, or why?
No,
why?
it's because we're picking up a pulse, and the pulse always is an increase in strength. So the pen goes up.
So then why would the interference go below? I mean, the car can't absorb.
Right, because we're actually being a bit too simple. We're dealing with an interferometer, not a total power system, in fact.
Then what does that say about the source of the interference versus the source of the pulsar, in terms of the quality of the electromagnetic radiation?
I think we're probably saying that the interference is multi-frequency. It hisses and it gurgles, whereas the pulsar stuff goes beat, beat, beat. I think that's right.
I'm not sure if that would define the difference between above the line. I don't know. Okay.
Remember, we're dealing with an interferometer, and an interferometer has bright and dark fringes.
I'll have to think about it. But then why wouldn't the car show up? Anyway.
I think that's as far as I can go to help
me
you
too.
answer
I can't
the-
think of anything. Thank you so much.
Thank you very much.